Why so glum? I thought the teacher said she's going to limit our homework. Not give us limit homework. But Victoria, are you amused? Veronica. My name is Veronica. All right. Hey, when we first started, our very first homework and conversation that we had about Unit 2.1 was using the calculator to complete. And what I want you to do is go back to this worksheet, and I want you to think about what's happening with each of these values. I'm getting closer and closer to what? To 2. I'm not reaching 2, just getting closer and closer and closer. And what I'm doing is I'm looking at what this outcome is getting closer to as a result. So we still want to go back to that idea of a function where I have what goes into the function as my input and what comes out of my function as my output, and know that f of x and y and my output are all the same thing. And that is what we're talking about with this idea of our limit. What are we approaching? What value is the output of our function approaching? We can approach that value from either the left, or if you think about it, we can approach that value from the right. Each time, again, I'm getting closer and closer to 2, and you needed to compare these values. When I plugged x is equal to 2 into my function, it went with no problem. We didn't have any denominator issues, so we were able to see that the value approaching from one direction and the other direction and the value were all the same. Going back, now that we've talked about limits, you can see how that was us showing you what we're doing with limits. If you look here, some trouble happened here because, of course, now we're talking about what happens when our denominator approaches the value of 0. If I have the value of 1 plugged in, I have a value that I'm approaching, whether I'm going from my left or from my right, I end up with that same value, except for here, I wind up with 0 in the denominator when I plug in the value, and we can't have that. So that first value here, when we plugged 1 in, and we remember we're not allowed to have 0 in the denominator, we want to make sure we know that that is a no. So that first homework had us exploring limits before you even realized it using tables. Well, we spent time talking about Euler's number. We spent time looking at the way that we can earn money, looking at interest. We compared the tables, and then we looked at Jacob Bernoulli's constant as n approaches infinity. As I start taking things to an infinite power, at the same time I'm having 1 plus infinity, we ended up exploring the fact that we end up closer and closer to this value of e, 2.71, blah, 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 that constant growth factor that we have. Okay. Our reference sheet reminds us, as x approaches, that's our input. What it's approaching is our output, that's our y value. If my limit from my left and right don't match, then the limit does not exist. When I go to find a limit algebraically, the most important thing is always to use direct substitution. Only when I end up with these indeterminate forms do I deal with all of the different ways I can manipulate a value. If I get 0 over the number, then the limit is 0. If I get the number over 0, then our limit does not exist. These are our indeterminate forms here 0 over 0 or infinity over infinity, where I'm going to end up dealing with these options. Factor and simplify, find a common denominator, use my conjugate, or use my trig rules. Here's your trig rules that you look at. And remember, we showed these graphs on Desmos so we can justify how each of those things ends up happening. When I have limits involving infinity, that's when I'm exploring that idea of a rational function, which is a polynomial over a polynomial. To find that limit, we look at the behavior of the numerator versus the behavior of the denominator. Because I'm involving infinity, it's difficult to plug infinity in, so we just have to look at the behavior of having a big number versus a very small number, and where in that value it is. If my higher degree is in my numerator, that's wrong. If the higher degree is in my denominator, then I have 1 over infinity. The bigger number I put in my denominator, the smaller my value, and that is why my limit is 0. If my degrees are the same, then I end up with infinity over infinity, which is going to cancel out and give me 1, which is why I'm going to end up looking at the ratio of the leading coefficients for my horizontal asymptote, and that ends up being my limit as x approaches positive and negative infinity. If the higher degree is greater than in the numerator than the denominator, then the limit does not exist. And we talked about why this ends up happening when you think about a slant asymptote. When you think about a function that has a slant asymptote, that limit as it goes on continues on forever to infinity. And sometimes people will say it does not exist, sometimes it's infinity. Adrian, this is what we talked about last time. Go ahead, thanks for waiting. Our last lesson was about continuity. And continuity is basically if you can trace the curve from start to finish, even if that curve does not continue on forever and ever, it can still be considered continuous. And what we need is these 3 things to exist for it to be continuous. I want my limit from the left to be the same as my limit from the right, and I want that to be the same as that numerical value of the function at that point. If all 3 of those things are the same value, then yes, it's continuous. The things that destroy continuity is if I have a hole in the graph, and if that value is defined somewhere else. If I have a jump in the graph, then that's a possibility too. If I have asymptotes in my graph, then it's not going to be continuous. And I'll go ahead and give you some coordinate planes so you can see what we're talking about. 3 different kinds of discontinuity. Is it a jump? Is it a hole? Is it an asymptote? All right. When we were looking at the limits using a graph, we talked about the value as it's approaching, and we had a good time talking about Mr. Ant walking on the graph. And the limit exists when both the left-hand and right-hand limits were equal. And you ended up adding a thought bubble about what you thought was important about that lesson. If you ever find an oscillating function, that limit does not exist. And then we played with lots of different times when our limits were different because of a jump. Our limits were the same because of a hole, or because of that value was defined, or the limits were the same even though the value did not exist. So we went ahead and did lots of reading of graphs and substitutions and creating graphs. That was tons of fun. Our first homework had us looking at graphical limits. and finding these limits using the graphs. When you look over your homework, any sticky spots, any things you want to go over, any things that were not answered, any things you want to talk about again. All right, so this was the graph. This was the homework where you had to sketch of the graph, and it had to satisfy all of these conditions. The easiest place to start is when you're talking about what the value of a function is. -2 goes in, 5 goes out. I know that that's going to be the first thing that I can put in, no problem. When I look at the rest, we want to make sure that we might end up doing a little bit of erasing. The limit as x approaches -2 is going to be 1. So as x approaches -2, the limit is going to be 1. The problem is, I already have that value defined, which means that's going to be a hole. Now, the line that I draw doesn't matter until I get through the rest of my considerations. I just know that from the left and the right, they need it 1, even though the function's defined somewhere else. Are you with me there? All right, and as x approaches 4 from the positive, my limit is 3. So I'm going to come up here. I don't know if it's defined as that yet, but I know from the positive, my limit's 3. So I can just draw that line to get me started. This is the tricky part. Okay, f is increasing as x is less than -2. So this line here has to go. I didn't do it right because my output of my function has to be increasing when x is less than -2. So I'm going to draw it down like that. As I move left to right, now it's increasing. Now I'm okay. So I got that taken care of. The limit as x approaches 4 from the negative has to be smaller than the limit as x approaches 4 from the positive. Okay, so that means that this as x approaches 4 from the positive, that's 3. This one wasn't 3 because this limit as x approaches 4 from the negative is less. So if I have something that looks like this, that'll be fine because this limit is smaller than this limit. This value is my only definite one, and I think I've met all of the requirements. Does that make sense? Do you want me to walk you through the next one too? Okay. An input of 1 gives me an output of 3. So I know that that's good to go. As x approaches 1, my limit from my left and right is -2. So that means that I've got this kind of scenario going on. As x approaches -3 from the positive, my limit is 5. Oh dear. So maybe I'll get rid of this because as x approaches -3 from the positive, so that kind of means that. G is increasing only between -5 and -3. So that means it's increasing here. And when x is bigger than 1. So over here, this has to be increasing. So we'll go ahead and make this increasing. The limit as x approaches 3 from the negative is bigger than when x approaches -3 from the positive. So I have the limit being the same. So that means that this has to be a smaller value, which means this has got to be here. And then we can say that. Did I get them all? Input of 1, output of 3. As x approaches 1 from both sides, my limit is -2. As x approaches -3 from the positive, oh, that's wrong. as x approaches -3 from the positive, my limit's 5. So I erased the wrong part. This one says the limit is 5. And then here, where it said that this limit was bigger, then this has to be here. What do you think? Did I fix it now? Because isn't this -3 from the negative bigger? So now I'm okay. Am I okay now? And it's only increasing from -5 to -3. And when x is greater than 1. I think I got it. So just take them one at a time and bring a big eraser. So when you look here, the first thing that you're going to deal with is going to be this one. This one is interesting because it has each of those 3 things together. We okay? All right. In our next lesson, we talked about evaluating the limit of the function using algebra. And what we realized that using a table of values and plugging things in, there's got to be an easier way. So what we do is we just plug in. And this is where our algebra and our order of operations comes into play. This is where we need to know our trig and our logs and our natural logs. And then we get these piecewise functions where during different pieces of the functions, it's a different rule. So we have to think real carefully about what input values are giving us. And if we wind up with different outcomes, then that limit does not exist. So the limit approaching -5 from one direction was not the same as from the other, so that whole limit does not exist. This one does exist because as I'm approaching E, though, as I'm approaching -1 from the left and right, I have the same value. My 3's matched. This practice we ended up doing on our Sage and Scribe, which was our partner 1 and 2 conversations. Lots of limit practice here for you to go back and fill in and check if you need. Okay. 2-3 homework. Using algebra to either multiply, add, subtract, or divide limits. Using algebra to substitute and simplify. Piecewise functions to calculate. And then graphs to determine. That was a nice review for your quiz. Next up, on 2-4, we talked about algebraic manipulation, because what we ended up realizing is sometimes when we went to find limits, we ended up with this thing happening, and we were like, wait, what? What do I do for that? And that's what I have in indeterminate form. So we look at our toolbox of what we can use, factoring, a common denominator, doing the conjugate. And this conjugate depends on my difference or my sum difference pattern. When we talk about why that works, this is our sum difference pattern. And the cool thing about that is it's always going to eliminate my radical and turn my sign from positive to negative, negative, positive to give me what I need. Now again, these are designed to work out. So you're always going to, in factoring, find something that's going to cancel out, and that's what eliminates the problem that you had by having a 0. By factoring, I'm going to eliminate my problem. By finding my common denominator, what always ends up happening is I wind up having a plus or a minus, and then an x that cancels out. And that's what makes the substituting work out now. What I'm doing is I'm eliminating a hole that caused all the problems. Our conjugate, because I had a minus here, I put a plus here, and that's what ends up giving me something that then works out and not having everything cancel out. So that way of manipulating things becomes very important. Okay. Using our trig to evaluate. Any questions on this homework that we had, or I believe this was classwork? Because your homework was here. Algebraically calculating. If you want to see any of these, let me know. I'll be glad to show you what you need to see. 14. All right, so when I look at 14 on 2,4, I see a conjugate. So if I multiply, well, if I do step 1 and plug 0 in first, 2 minus the square root of 4 plus 0 over 0 is going to give me 2 minus 2, which is 0 over 0, and that's my problem. All right, so then to solve, I'm going to go ahead and 2 plus square root of 4 plus x, 2 plus the square root of 4 plus x. This is the conjugate. I had a minus, now I'm doing a plus. That's that sum difference that makes that middle term cancel out when I multiply. That's me on purpose picking something that I know is going to work out. I'm totally taking advantage of a property of algebra that I know works. When I multiply these factors, 2 times 2 is 4. 2 times this mess is 2 times square root of 4 plus x. When I do this, it's 2 times negative square root of 4 plus x. Those are a 0 pair. I'm not even going to bother writing them down. So now when I multiply my last terms, a negative times a positive is a negative. And the square root of 4 plus x squared is just 4 plus x. I on purpose picked the very thing algebraically that was going to eliminate the radical from that conversation. Next up, x times 2 plus the square root of 4 plus x. And this is where you're worried. Here's why don't be worried. A, two things here. Do not distribute that x because he's going to end up canceling out. How do I know he's going to cancel out? I've done 4 or 5 or 600 of these, and I know that's what's coming. We're going to lose x. Because that's what's going to solve our problems. Number 2, I'm not worried about this radical because look, now I have this plus sign, and I was in trouble before when it was 2 minus 2, but now it's going to be 2 plus 2. So I'm not going to get a 0. So the conjugate is solving all the problems. All right, ready? 4 minus 4 plus x gives me x in my numerator because 4 minus 4. Except this negative gets distributed, so don't forget that's a negative x. In my denominator, I have x times 2 plus the square root of 4 plus x. And I told you he was going to cancel out. So he was our first problem because when I multiply anything by 0, I get 0. That's why that 0 in the denominator. That's bad news. Okay. Now when I have negative 1 over 2 plus square root of 4 plus x, when I go to substitute 0 in for x, I get negative 1 over 4. Square root of 4 is 2, 2 plus 2 is 4. Now I have an answer. The conjugate saved the day. Feel better, Anthony?
Yes, about that.
All right. After we talked about manipulation, we reviewed rational functions, and then we went ahead and talked about limits to infinity. And the reason why we care about those rational functions is because every time I end up with a vertical or a horizontal asymptote, it changes my graph and it affects my limits. So looking at where that horizontal asymptote is, talks about where my function is going as x approaches positive and negative infinity. I can't plug infinity in, so what I need to think about is I'm actually plugging in each time a bigger and bigger and bigger and bigger number. If that big number is in the denominator, my value is getting smaller and smaller and smaller, approaching 0. If that value is in my numerator, then my value is getting bigger and bigger and bigger, approaching infinity. If I have the same powers, then I'm approaching 1. I'm just looking at the coefficient, the fraction created by the coefficient. So this makes sense to me when I see about a super big number in the numerator or denominator and that output. So this part of the notes makes the most sense to me. We did this partner activity where you guys got the same answer, partner A, partner B, doing lots of practice. We went over the homework. And then we started talking about continuity. In our conversations about continuity, we're paying close attention to where do things go wonky with the graph? Where are there holes? Where are there vertical asymptotes? Where are there horizontal asymptotes? Where is my graph going? With each of these different conversations, paying attention to where those horizontal asymptotes are telling us where the continuity fails. Now, if it's a function with nothing in the denominator, then I have a continuous function. So our formal definition of continuity is if my value is defined and I have no holes, if my limit exists for the positive and the negative side, and if these two things are the same, then I know my function's continuous. So the kind of questions we ask you are, is it continuous at these values? State whether the function's continuous at the given x values. So let's go ahead and talk about this one. If I were to think about my number line, I can tell I have some crazy stuff happening at -1 and at 2. If my value is less than -1, my input value, this is the function that I'm using. If it's greater than or equal to -1, but less than 2, that's the function I'm using. If it's greater than or equal to 2, that's the function I'm using. So if I want to see what's going on at this input value, if I want to see if it's continuous, I need 3 pieces of information. I need to know the limit from the left, I need to know the limit from the right, and I need the value of the function at that spot. So when I'm talking about the limit from the left, I have to use the x squared minus 2x plus 1. So when I figure out that limit as x approaches -1 from the left, I'm going to go ahead and put -1 into this expression. -1 squared minus 2 times -1 plus 1. 1 plus 2 plus 1 sounds like 4 to me. Are we okay? Now I need to know the limit as x approaches -1, but from the positive side. Because I'm coming at -1 from the positive side, I'm looking at this way, so I need to use this function. So I'm going to say -1 plus 2 is equal to 1. Already I know I'm not continuous. Because at -1, these two output values don't match. So we can go ahead and say, therefore, it's not continuous. At x is equal to -1. Okay? All right. We didn't do this together as a group, so would you please, with your partner, go ahead and determine if x is continuous at 2. Is the function continuous at 2? Turn and talk to your friends and say, all right, are you ready? How do we do this? Turn and talk, go. We're on the notes. It's not the homework. Do you have the notes? That's all.
Oh, yeah.
Do we agree? Okay. So this was a little weird, especially when you feel like you're duplicating your efforts, because here x is greater than or equal to 2. So really, we know that that value is equal to that function at that. So I kind of did the same math twice. That's not always the case. So you have to make sure that you can think of it as 3 different considerations. Sound okay? Yeah? All right. Then you had your continuity homework. So what I'd like you to do is I'd like you to take a look over the work that you did in my answer key. I'm going to give you a couple minutes to come up with questions, and I'll be glad to go back over and answer whatever you need. So we had a great question in the back from Stephen. He's like, how are we supposed to know? How are we supposed to know? It says, for each function, identify the type of discontinuity that anywhere is located. Like, how are we supposed to know if we don't have decimals and we're not second in line? And this is where we have to kind of be smart, and we have to know what's coming. Basically, and this is what we need you to realize, anytime you have a variable in the denominator, you're going to have an asymptote. So take notes on this. If it helps you, first of all, if you have an x in the not these. X in the denominator, then you're going to have a vertical asymptote. Every time you have a vertical asymptote, you have a discontinuous function. Okay? But before you can go ahead and declare every single x in the denominator a vertical asymptote, you have to right now see if there is a place you can factor and cancel out that x. Because if he cancels, guess what? You have a hole. So if he cancels, you have a hole. Now, we don't worry about jumps until we end up looking at places like these on the back. This is where you're exploring your jumps. This is where you're exploring, is the function in different pieces all over the place? Because remember, what we want to do is be able to trace our pencil across the entire length of the graph. And these piecewise functions are tricky. If they don't match up and continue on, then that's going to be a point of discontinuity. All right, let's zip through these. Ready? If I go ahead and I take this graph and I say x squared over x times x plus 3, I can cancel out this x with one of those. Which means I lost one of my x's that causes a vertical asymptote. So originally, you might have thought that x is equal to 0 and x is equal to -3 are where our vertical asymptotes are. But once I canceled this out, now I know that that's a hole. Okay? So if I have a vertical asymptote where the graph is equal to 0 in the denominator, I know at x is equal to 3, this graph is discontinuous. One side of it goes on to positive infinity, one side goes on to negative infinity. So I'm not going to be able to trace that whole graph with my pencil. Let's talk about this hole. If I want to deal with this hole, I know that if I have an input value of 0, it used to cause an asymptote, but that canceled out. So now I have to look at the value of the function at that. So I'm going to substitute into my function 0 over 0 plus 3, which means my hole is at 0, 0. You okay with that? When we look at number 2, I have nothing in the denominator, no variables down here, so there's no time that this is not going to be continuous. So this is continuous. And someone says, well, why don't you factor it? Well, I can, but all that factoring is going to do is tell me where my solutions are. This graph has 3 solutions. If I were to graph it, my solutions are at 0, positive 2, and negative 2. It's a cubic function, so it continues like that. I can draw that whole graph without picking up my pencil. It's continuous. No asymptotes. So the factoring that you can do here doesn't mean anything. It just tells you where your zeros are, but there's no asymptotes there. You can trace the whole graph, no problem. I know here I have a vertical asymptote potentially at x is equal to -3. But let's go ahead and factor this and see if that ends up becoming a hole. If I have +3 and -1, yep. That means that this factor cancels out, which means that's not a vertical asymptote, it's actually a hole. And if I want to know where the hole is, I have an input value of -3, and I'm going to put -3 in there, and I'm going to see that -4 comes out. And that's going to be where that hole is. This graph is going to look like x minus 1. It's going to look like a linear equation, the slope of 1 and an intercept of negative 1. But little do we know that at negative 3, 4, there's a hole. I can't trace the whole thing with my pencil. I have to skip over that hole where it's undefined. X plus 2 over x minus 4 plus 2. Hey, y'all, these are designed to work out. So use some of those hints for your factoring. What I end up with here is my vertical asymptote at x is equal to 4, because that's where my denominator equals 0. And I'll have my hole at where I went ahead and was able to remove whatever caused a 0 here. So negative 2 as an x value. And then when I put negative 2 in, if I have 1 over negative 2 minus 4, that gives me negative 6. So that's the xy orbit pair of where I know that function is not defined. Knowing where your vertical asymptote is, checking to see if it's a hole can tell you whether or not it's continuous. Scan down this homework. Anything that you want me to go over that you had a hard time figuring out? Go ahead. Oh, yeah. Oh, here's your Smarty. Nice. That was the last one you needed. So today's activity is why you're all in groups. So here's an answer sheet for each of you. All right, so clear off your desk. So what you're going to do is you're going to rotate from group to group and answer the question. So here I have group 1 discussion questions. So say this with me. I'm not going to write on the colored paper. Say it again. I'm not writing on the colored paper. I'm not writing on the colored paper. So this group is found in color. So what's going to happen is they're each going to be able to look at it, right? And then they're going to be able to have a conversation about it, and they're going to answer on their answer sheets. Then they're going to go to a table that's open. So maybe they'll go to this table next that's open, and then they'll answer the second question. So you're going to float around the room. Hopefully it'll work out that everybody should get to each group. And as you finish, you'll find a group that's open and they're rotating around. So you're not going to maybe go in order, but there's one open group. In fact, I might end up, let's create 2 open groups. So Simon, I'm going to have you go sit next to Brady, and then Stephen, when she sits next to Ricardo, so there'll be 2 open groups. Does that make sense? Here you go. Here's the purple group. Clear all this stuff up. And clear your stuff off. Kind of pack up your stuff a little bit so that your neighbors and friends can come in and sit at your group. So let me go through this one more time. Make sure everyone's listening. Alright. We have 1, 2, 3, 4, 5, 6 groups. Point to the groups where no one is sitting. There you go. So when your group finishes, you leave your colored pieces of paper and you go to one of the open groups. How's that sound? Any questions before I let you go? Are you marking that slide? Yeah, it's just what happens at the same time. So good. So that active function which is the following conditions explains why everything is. So what I want you to do is this is a function. One of these cases will justify why it's not happening. So your answer is A, B, or C, but you have to justify. So for the question, you have to, I want to sketch a graph and I want you to say, tell me why it doesn't work. Does that make sense? I put a tab in. I wasn't sure.
Ellen is
So then what you want to do is on your workspace, you have them each other, and then you can.
oh yes.
No, you probably did it right.
Okay, so I find
You have.
I okay. What I do. I like this. That's too simple. No, love.
I'm just copying. Two. What are the three?
Yeah. Yeah.
So if K is equal to 6,
Wait.
if K is equal to 6, they come out to be the same value.
No.
Yeah, that's what I had. Say the exact same thing.
That one,
Yeah.
So if k is equal to negative 17, then this function will meet up.
Nothing.
Why did everyone else get so small?